uh, uh, scheduling is basically is assigning time step to the operations, right? Robotic. So, and then we have seen that we found that particular scheduling is actually an NP complete problem. It's basically that means there is no polynomial time algorithm available to solve the problem, right? Which means if you try to solve it exactly, you need kind of exponential solution. And so far for we have discussed how we can model the scheduling problem as a integer linear programming problem, right? So although I have declared that we will have a demo today, but the demo is still not ready. So next Friday we'll show the demo. But today we'll continue this formula. So in for general purpose scheduling, we assume we have shown that how to model that an ILP, and there are two kind of formulation we have checked in last two classes. One is MLRC and one is MRLC, right? Minimize latency under resource constraint or minimize resource under latency constraint. That's the dual problem. Today we try to see a specific class of scheduling problem. In general, uh, general problem is hard, right? So it's a compression hard problem. In today's class, what we try to see, if we try to take a subset of that problem, or we try to make some assumptions on that particular scheduling problem, and then we'll see how whether that particular subset of that class of problems of scheduling problem is polynomial solvable or not, right? So one class is basically multiprocessor scheduling. Okay, so multiprocessor is what? The first assumption is that the arithmetic unit is a multiprocessor unit. What does it mean? Basically, I have a single type of function unit, right? I do not have a multiplier or a adder or subtractor. I have a multiprocessor which can perform any operation. It's just like our generic processors, right? It's a multiprocessor. It can do any operation. So the first assumption is that all the operations have the same type, right? So it's basically a multiprocessor is executing all the operations. So that means that particular resource type, different type of resource problem in that particular thing, we actually make a restriction that I am not going to take different type of resources, rather I will have a single type of resource only, okay, and which is a multiprocessor unit. So that's the first assumption. The second assumption is all operations have unit delay. So earlier with the generic formulation that we have seen is basically where the operation can have multiple delay, and we have seen that the delay is represented by di for each operations, right? So under these two assumption, let us try to see. Unfortunately, for these two assumption also, the problem still remain NP complete, right? It cannot be solved by, I mean, it cannot be solved in polynomial time, okay, by a deterministic algorithm. So let us just to see the ILP formulation for this multiprocessor scheduling. I am going to talk about this MLRC, and you can actually just think of this MRLC easily, because this is, I will just try to present this MLRC here, and MRLC is kind of your homework. Okay. So under these two assumptions, the first assumption is that I have a single type of resource, no different type of resource, and all operations are single cycle, right? So under these two assumptions, if we try to find out this, try to formulate this ILP formulation for MLRC, so what will be our objective function? I try to find out the start time t. So t is again a vector of the start time of the all operations, and c is basically a vector of constant, and we have already argued on that to minimize latency for a given resource constraint. This is nothing but all zero, but the last value is 1. Basically, it does it mean we try to find out the earliest execution time of the sync node tn, which implies that we try to, that is the minimum possible schedule, or that will give you, that will actually minimize the latency, that we have argued, and I'm not going to argue further. Okay, so, and we remember that for ILP formulation we have taken a variable xil, which is nothing but this uh, if a particular operation I vi scheduling time step l, right? So I'm going to use the same variable again, and this is basically, this constant says this unique start time means all operations can only start in one time step, it cannot start in multiple time step. And if you remember, if you just look compare with the general formulation that we have already seen, I just copy paste the things here just to correlate. It is remains same, right? The unique start time cannot change, so unique start time constant remain the same, and this xil is a boolean variable, that is also the same, right? So this first part, objective function remain the same, unique start time uh, constant also remain the same because it does not vary with the unit delay or same type of resource, right? Let's now check the data dependency constant. So for general purpose, we have seen that basically it is what says that for each dependency, there is a age from Vi to Vj. We have to make sure that, sorry, it is from Vj to Vi. We have to make sure that Vi can only start when Vj is completed his execution, right? So if Tj is the start time of Vj, the Tj plus Dj will be the start time for Vi, right? So that is what when we can represent the Ti and Tj in terms of xil that we have already discussed. So the constant was look like this, right? And Dj is the execution time for node Vj, right? Now if we just simplify this, because here the Dj is always 1 for me because this is a unit type operation. So other things are remain same, right? So if I just rewrite the things from this, I just replace this Dj with 1. So that will give me the data dependency constant because here my delay is unit delay, right, for our operation, right? So this is data dependency constant. Similarly, for resource constant, if we take the general purpose, what we have tried to find out this equation, try to find out for each type of resources, we have n resource type of resources. For each resource type k, I try to in a particular time step L, this particular summation will give you what are the operation that is actually active in time step L, and I'm trying to see that for each type of resource in every timestamp, the number of active operation of that type will be under the resource bound, right? So that is what is this equation express, and we have already discussed in detail. So now if you try to simplify this for our cases, here this equation will simplify because AK, there is no AK, I have only a single resource. This is not a neither vector. So this term will not be there because all is basically all operation of the same type, right? So similar type. So, and I have a single constant bound A. And I don't need to calculate this summation also because here all operation, this di is 1, so if we just put di equal to 1, it's L to L, so it's there is no summation, it's just the xim, right? So what I have to see, I have to see for every timestamp L, I have to see what are the operations start this execution or basically is going to execute in timestamp L, which should be given by this, which should be less than the resource bound, right? So this is much simpler constant, but this remains, it will still represent the same resource constant, right? So that's all that we have this unique start time, which is same as the general purpose for formulation. Data dependency is exactly same, only dj is replaced by 1, and resource constant get much simplified because here all operations are unit delay, and there is no multiple resources, there are single resource, right? So if we just formulate this way, then it's actually solve the MLRC problem for multiprocessor scheduling, right? So this is what the ILP formulation. But as I mentioned, this is still remain as the NP complete problem. In this proof, we can just assume because this is a generic course, but if interested, we can actually go into detail. But the problem will remain NP complete even under these two assumptions, right? So in this way, we can also formulate the MLRC problem also, right? So we already know that, and we can always write the corresponding multiprocessor version of ILP formulation of MLRC from that. I hope you can do that easily at home, right? So as I mentioned that under these two assumptions, this A1 and A2, the problem still remain NP complete, right? So now we'll take this third assumption. Okay, this is a specific kind of assumption where I'm saying that my dependency graph is a tree. Okay, so this is very important. So I'm saying that I still have a single type of resource. That means I am using a multiprocessor to execute all operations. I am saying all operations have a unit delay, and I'm saying the sequence graph is tree. Again, this is the sequence graph is not tree in for all cases, obviously. Tree means what? There is a unique path between any two nodes, right? There is no two parallel paths. So if you consider in dependency graph, if you consider any two nodes, in general cases, you might have parallel edges, right? So for example, suppose you have considered like this, and say, so you might have some edge to this, and then you can have a edge like directly like this, right? So this particular operation depends on the output of this operation plus the output of this. It can happen, right? So but this kind of parallel edges is in parallel path is not possible in tree, but it may be in some cases. In fact, the graph that I'm taking in all the example, the DIFFQ example, is actually a tree, right? It's not something, there is no parallel path. I mean, I'll show you the example again in next slide. So if in a particular case, when you have the sequence graph, which is basically a tree, we can actually solve this problem in polynomial time. That is the uh, biggest takeaway for this kind of assumptions, right? So in a particular specific case of scheduling, when we have a multiprocessor scheduler, we have all operations is single delay, and the sequence graph is a tree. It's so that means there is no parallel paths. Have it makes sure that this problem can be solved in polynomial time, right? So for so then we actually saw this. We can have exact solution, and which is kind of greedy strategy, but it will make sure that it actually give you the optimal solution always in polynomial time. And one of the famous algorithm is Hughes algorithm to solve this particular problem under these three assumptions, right? This is what we are going to discuss in today. Although you might argue that what is the need of discussing this, because this may not be, it's not solve the general purpose problem. But as I mentioned, this NP complete problem for general purpose graph, for general purpose sequence graph, the problem is NP complete. So for that, don't have a polynomial time algorithm, but so we need a heuristic solution, right? Heuristic solution is something which is very fast, which is polynomial time. It does not guarantee the exact solution, but optimal solution, but it gives good solution most of the time, right? So we'll see that for general purpose scheduling, where the operation have a different type of resource, it is does not have, hold the assumption one, it does not hold the assumption two, that the operation has a unit delay, it does not hold the assumption three. Uh, so in assumption three, so in that case, the most useful scheduling algorithm, the heuristic based scheduling algorithm, comes from the idea of Hughes algorithm, right? So that kind of take the Hughes algorithm and then I mean come up with a heuristic, right? So that is why this particular algorithm is very important to understand, because the heuristic solution based on this idea. Okay, so let us go into that. So we have to keep in mind these three assumptions all the time, that our operators are a single type, it's a multiprocessor is executing them. All operations is a unit delay, and the sequence graph is a tree. Okay. So when if somebody is to argue why this problem is P, the reason is this: that you always have a single path from each vertex to the sync node, where if you just put the some level, which is level is nothing but the path length from the sync node, it will be always monotonically unit wise decreasing. It's a unit wise, right? So there is no 2 to 4 jump, right? So because of that property, this particular problem become P. But let's not go into that theoretical aspect of this problem. Let us discuss the algorithm first. Okay. So
Sir, what is P, sir? Like, what does
P
P
is the
represent?
polynomial time solvable. So what we have algorithm is
Sir,
complex.
could you repeat once again? Your voice is feeble.
Yeah. So polynomial time solvable means you can write an algorithm whose complexity is n to the power k, right? So n is the number of the problem size, right? So here the number of node you can say. So which is basically n to the power k, k is some constant, right? So if you have an algorithm which is its complexity n to the power k, say order of n square, order of log n log n, these are all polynomial algorithm. Just like sorting have, right, this n log n or say n square algorithm. So those are all polynomial time, right? Deterministic polynomial time solvable, right? And
Okay, sir.
NP completes something which is basically complexity is k to the power n. So here k is constant and n is the problem size. right? So that means we say exponential solvent, right? So 2 to the power n or say 10 to the power n or those kind of algorithms are basically exponential algorithms. So which is basically won't in practice. I mean, you cannot apply those algorithms in practice because it's a huge complexity, right? So yeah. So let us now move into the this labeling part, because this algorithm works on a particular labeling of the nodes. So labeling is something, as I mentioned in the previous slide also, that is basically use identify the longest path from the sink to a particular node, right? So you know the sink node, you see what is the length of the path. There may be from the sink node, what is the longest path, and then you find out uh, that particular value is the level of that node, right? So let us assume that alpha is the level of a particular node I. Okay, so alpha is the length of the longest path from the sink node to that particular node vi. Okay, and alpha is the maximum of all such leveling, right? Obviously alpha will be the level of some the almost the source node or the node that is actually longest distance from the sink node. That means the first level node. This must be the first level node, right? And this pj, we need to understand this, we need to remember this terminology, because I'm going to give a proof that this algorithm is actually I mean, is optimal. So remembering this particular term is very important. Alpha is the level of that node, which is the distance from the sink node. Alpha is the max of all such level, right? So the node has the maximum level. Pj is the number of vertices that has level is j, right? So if the level, so I will try to find out the number of nodes whose level is j. I am going to collect them, and this pj is that summation. So formally is basically pj is the all the vi whose alpha I is basically j. Alpha is the level of that node vi, right? So if the alpha is j, I am going to collect them, and pj is that summation or the sum of such nodes, right? The number. And one more important thing is that since all are here unit delay operations, they're all operation is going to execute in single cycle. So the latency, whatever is given by the lambda, so lambda will be always uh, greater than or equal to the weight of the longest path. So it must be greater than equal to alpha, right? So alpha is the max, right? So so this lambda, whatever the latency or the schedule time, the maximum schedule time that you're going to get should be at least alpha, right? So that is something is always hold, right? So let us take the yeah.
Thing. Here you are assuming the graph is directed, right? So when you're saying it's a tree, you're assuming there's no cycles, right? It's not it's not so much so that from one node you could reach the sink in two different ways, but that there's no cycle is the important assumption, right?
Yes, yes, yeah, yeah.
No, sir. What he said is wrong, right? Cycle will anyways never be there since it's a directed graph.
Yeah, it is a directed graph, and so basically it is tree means you have exactly n minus 1 edges in the graph. If there are n number of nodes, you have exactly n minus 1 number of edges. So the example that you have taken, it has also n minus 1 number of edges. It basically, there is not more than, the tree definition is between any two nodes, there is no two path, right? And this is a directed graph, so you cannot consider a path from sink node to this direction, right? This is not a path because there is an edge direction.
So, but is a like, because you're saying it's a tree and there are only n minus one edges, even in this directed graph, from 1 to n there can't be a direct edge, is what you're saying.
Yes, yes. So you cannot have a edge like this. So then it's a problem, right? So you already have a path here. I cannot have this edge allowed. Understood? Yes. So yeah. So just a minute. Huh. So now let us take the example, our favorite example, DIFQ, and let us calculate this alpha I for those nodes, right? So you can understand the alpha of this node is 0, this is 1, this is 2, this is 3, this is 4, this is also 4, this is 2, this is 3, this is also, this is 1, this is 1, this is 2, and this is 2, right? So because these are the alpha is the, which is 4 here. So for this example, alpha is 4, right? And how many is P0? P0 is 1 because I have only one node with alpha is equal to 0. How many are with P1? 1, 2, and 3. So I have 3 nodes with distance or with alpha equal to 1. Similarly, P2 is 4 because 1, 2, 3, 4. Right? So P2 is 4. P3 is 2. There are 2 nodes with of the alpha value 2, and sorry, alpha value is 3, and there are 2 nodes which has alpha I value is 4, so P4 is equal to 2. So it's very important to understand this. I mean, just to keep remember is these things, because otherwise the rest of the discussion it will be difficult to follow, right? So it's basically this number alpha I is the distance of that node from the sync node, and or basically the longest path or the distance, and then alpha is the maximum of such number, right? So here I just put the red numbers is the alpha I value for each node, and P is the summation of all such node. Pi is the summation of all such node whose alpha I value is I, right? So here P0 is 1, P1 is 3, and so on. So obviously you understand here that P4 is 2. That means these are the node which is basically has the maximum alpha value, and alpha is basically 4, right? So if you consider this way that if you consider this way that alpha is basically when you try to schedule these things with this if in alpha equal to 4 or say 4 time step, these are the 2 operation has to be scheduled in time step and 1 and so on, right? So this is something these things this particular labeling means. Okay, I hope this you understand this. So now let us understand this Hughes algorithm, how the algorithm works first. Okay, after that we'll see how what is the relations of these values and all. Okay, the algorithm is very simple. It's a greedy algorithm. Greedy is what? So basically you take a local decision, and local decision ensures the global optimize, right? So this is the greedy approach, and I mean I hope you all familiar with this greedy approach, right? Basically you take a local minimum decisions based on your current situation. You take the maximum, what is the optimal solution from the current context, but you keep doing that iteratively and make sure that whatever the solution you're going to get, that is actually the global optimal solution, right? So what this particular algorithm works that way. So I have given a bar of resources, right? So this will be a single number. Say I have given this equal to say 3. So I have given 3 multiprocessor unit. So that means I can execute at most 3 number of operations at a time. It can be 2, 3, 4, 5, whatever it is. I'm just assuming some number, right? It's a single constant number, which is the number of multiprocessor unit is available in your hardware. Okay, and so we first label the operations the way I did here, and then what I'm going to do, I just try to schedule from time step 1, 2, 3, 4, and so on, right? So I start my scheduling from time step 1, L equal to 1, and I'm going to do this particular loop until all operation gets scheduled, right? So repeat until all operations are scheduled. I'm going to do these things in loop. Okay, so what I'm going to do is I'll see what are the operation is schedule level, right? So schedule level is what? When his all predecessors are already scheduled. Okay, so in this example we have already seen earlier that this 5 node 1, 2, 6, 8, and 10, they are schedule level in time step 1 because they are actually depends on input, and we can assume that inputs are available at that point. Okay, so we'll try to find out all predecessors. So we'll try to find out a set of operations which is basically schedulable in this time step, and that is S, and that is basically so schedulable means all predecessors are scheduled. So I'll identify in time step 1 these 5 operations, and I'm going to select because I have a resource bar is a bar, so I cannot schedule all 5. I have to select 3, right? So what I'm going to do, I'm going to select 3 operation from this 5 such that the maximal of levels, right? So I want to, if I sum the levels of those nodes, that will give me the maximum value, right? So if you go back to this example, this is 4, 4, 3, 2, 2. So I must select this one, and this one. This is the only solution. There is no other alternative, right? Because then the summation of the level will be 4 plus 4 plus 3 is 11, any other subset, 3 out of 5, the total summation of that level will be less. So you understand that I'm going to schedule the operation which is have a more operation to remain to schedule, because the path is more means there are many operations that remain to schedule in that path. So I am giving highest priority of those nodes which has the highest value of level, right? So the idea is very simple. You in every time step you identify a subset of node A such that which is satisfy the resource bound. In some cases, you might have a selection which is less than A also. It might happen. Then there is no other choice. You just schedule them, right? But in general, if the S is more than the number of resource bound, you select those which is basically give the maximal of this level, summation of the level, right? And then you just schedule those operation in the time step L, and then you go to the next step. Right? A very simple algorithm. So this is the greedy decision. So among 5, I am going to select this 3. This is the greedy choice. But that greedy choice ensures that once you execute the whole thing, that will give you the minimum latency for a given set of resources. Right? So that is what is important. So that is why this algorithm is order of n. If you see, this algorithm is order of n, right? Complexity is order of n only. N is the number of nodes, because every node is considered. Every time I'm going to schedule some operations, and I'm going to complete this whole thing once all the operation is going to schedule. So it is complexity is basically nothing but order of n. So very first algorithm, and it is making sure that this particular solution actually meets the, I mean, give you the minimum latency under resource constraint. And then you'll also argue that, I mean, I'm going to take the same next, I mean, I'm going to discuss certain things, and then we'll argue that if the latency bound is given to me, it always meet the resource, minimum resource lower bound. Okay. So it's basically solve both. I mean, in context, it's basically it also in solver solves both in the sense that it also minimize the resource as well as minimize the latency. I'll come into that particular point. Don't get
Excuse me,
lost.
sir.
Yeah, please.
Sir, we took an assumption that like time for each operation is 1 unit. Like we can actually drop that assumption if we like change that a little bit when we are taking all predecessors are scheduled. If we change this line to, let's say, like which are we just have to remove which are currently going on or are completed. We can remove that assumption that only one time unit is required for each operation.
It's a good question actually. So yeah, so you might argue what is the point of considering the delay is one here, right? So it's a very good question. So what I'll argue, and probably I'll conclude this today's class with this particular argument, that if we assume that, then this exactness, whatever I just talked about, that this both it actually Hughes algorithm is both optimal in terms of latency as well as the resource bound. But if you consider that particular problem when your delay is not unit, it actually solved the MRLC, right? It actually reduced, I mean, optimize the, it gives the optimal solution for MRLC, that will minimize resource under latency constant, but not the other one, MRLC. Okay, so why all those things? Wait for 10 minutes. I mean, once I'm going to talk about those, you'll understand. But when if the assumption 2 is not there, not both MRLC and whose algorithm does not give optimal solution for both. Okay, so you can always consider, create a counter example that for that particular Hughes algorithm will give you the best solution. Okay, yeah. So let us solve this. How this works? So as I take this, my resource bound is 3. And these are the level. Yeah, I got disconnected in between, I guess. Yeah. So let me. I mean, I hope. Can you hear me now?
Yes, sir. Yes, sir.
Yeah, so I got. So don't mute me and all those things, right? This actually create unnecessary. Don't behave like a child, right? It's basically we are all matured and don't do this kind of nonsense. Okay, somebody just muted me. I mean, don't do these things. If you don't want to, you leave. I mean, you might lose 10 marks, right? Don't disturb others. You might be a big shot, but not everybody, right? Let us discuss the basic stuff. And I got very much irritated by this kind of nonsense thing. Anyway, uh, so uh, uh, yeah, so let me take the attendance first. Yeah, so let's continue. So what I was, the question was, I hope it's clear. So that for unit delay, the problem is exact for both MLRC and MRLC. But if the delay is not unit, then it does not solve the second problem, right? So we'll come back to those discussion in detail later. Okay. So let us work on this particular example that we already know the alpha I value for this node. So in first time step, we know that there are 4 operations is schedulable, and I'm going to select these 3 because that will be the maximum value of the level summation. And the next time step, these 4 operations are schedulable, so I have to select uh, 3 of them. So I'm going to select this must and any 2 of these, right? Because I mean any 2 is with the solution, so you can select any of them. It doesn't matter. So let me schedule this 3 say. Right, so now this operation 3, 7 and 8 is done. So next time step I have exactly 3 operation is schedulable, and I'm going to schedule them in next time, right? And then in the next time step 2 are schedulable. I have 3 resource, but I can help. I'm going to schedule these 2, right? So this is a schedule which will be given by the Hughes algorithm for this particular graph. Okay, I hope everybody understand the algorithm.
Yes, sir.
Yeah. Good. Yeah. So now let us go to this leveling thing I have already discussed. So let us skip this. So these are already discussed that this is the level and all. Now let us move to the theorem part. Right. So the understand the value of this Hughes algorithm. So what is important that we can actually given a lambda. Lambda is the latency bound. Right. So latency, I can identify a lower bound of resources. So that is given by this equation. I'm going to discuss this equation in detail. Don't worry about the numbers here. So which is something, say that given a latency bound, I can calculate a lower bound of resource. Okay, which is basically again is basically in terms of latency also, right? And here you remember that p I or p some number is nothing but the summation of those values I, right? So alpha I, and I'm going to take some gamma, which for some such gamma for which it will give the maximum, that is my lower resource bound, right? Will give some maximum integer constant, say gamma, that is my lower bound. So let us solve that problem. Okay. So this is something, okay, let me just give the theorem first, and then I'll go into the proofs and other part. So what is important for this, under these 3 assumptions, given a latency, I can identify a lower bound of resource by this just applying the equation. I'm going to see so that why this theorem is correct. So that is my theorem 1. And the beauty of this particular Hughes algorithm lies on these two theorem 2 and 1 corollary is something that if we applied this particular graph to a unit this with a resource, it actually achieves the minimum latency. That means it is basically minimize latency under resource constraint. So given this lower bound of resource, and if I give some value lambda, it actually always able to solve the problem in lambda. So what does it mean? So if given a resource bound, it always give you the minimum latency. So it actually solves the problem MLRC. Okay. In the other hand, if you see, if we since A is the lower bound of the number of resources, right? For this, I can always say that this is also solve the problem of MRLC, because if I give the latency bound lambda, so and I know for this lambda this is my minimum resource, so obviously it is also solving the problem of MRP. So under these three assumptions, both this algorithm. So what the interpretation of my statement, that if I know the lower bound, I mean I can make sure that this Hughes algorithm always is able to schedule the graph in lambda time step using a bar number of resources. So where a bar is the lower bound and lambda is also is achievable. So this is basically both exact in terms of resource as well as latency. Okay. I hope you understand this. So let us try to understand this lower bound, how you obtain this lower bound, right? And what does it mean actually? What this particular expression means? Okay. So with the terms of our example. So how we get the lower bound? Let's try to understand. So if you so you know that, so the particular the operation that with the highest p4, right? So for this example we have the p4 is the highest value. You
Excuse me,
remember?
sir.
Sir,
Yes.
which slide are you in?
Are you in exactness of use algorithm slide only?
I'm in 49 now.
So could you reshare it, because for it's stuck for me. I don't know about others, but it isn't. It
Yeah,
didn't change for me.
I'll do that. I'll do that in a. Is my screen visible?
Yes, sir.
Yes, sir.
Okay. So as I mentioned that given a latency number lambda, I can actually identify the lower bound. The theorem says that only. So let us try to understand that, which what does this mean? So if you see here, so this gamma is some constant. That is what, for such constant value, this expression give me the highest value. So I'm going to find out that gamma. So gamma is important, right? So when once the gamma is 1, what does it mean? So if we just put gamma equal to 1 here, so it's basically and in this particular example, if you remember that alpha equal to 4, right? Alpha is the max of leveling, and let's say my lambda equal to 4, because I already solved the problem for 4. I know this particular graph 4 is the minimum. We already know those values, right? So if we just consider this value, so if my this gamma equal to 1, then this is basically, this turns out to be 0, so it is basically just 1, right? And here gamma is 1, so this is just basically, if you put here j equal to 1, it is nothing but p4, right? This is p4. So once you put this gamma equal to 1, this is by p4 by 1. So it's basically, it says that all the node has the highest number of alpha value. This, I mean, what is the number of resource needed? So this is nothing but this, right? So now if you take gamma equal to 2, so then what will happen? So here gamma equal to 2, and this is basically 0. So it is basically the lower part is 2, and here it is the summation will go for 1 to 2, and for that it is once I know that whenever gamma equal to 1, this is p4, and whenever gamma equal to 2, if I just so j equal to 2, it is basically alpha minus 1, so it is p3, right? So that means it is p4 plus p3 by 2. So again, if you just go this way, if we put gamma equal to 3, so this is actually 3, this is a mistake here. So this is basically p4 plus p3 plus p2 by 3, and this is when you put gamma equal to 4, then it will become p4 plus p3 plus p2 plus p1 by 4. Okay, so basically after that you cannot have value, because this will become if we put so because we have maximum p4, so p4 to p1, so I don't need to consider any gamma value beyond 4. Okay, so what is this interpretation? It means you take, if you just take the highest value, you take, I mean, you need a resource at least to execute this, because this has to be executed in the time step 1. So this need at least this number of resources. Or it may be the case that P4 is less but P3 is many. So you take P4 plus P3 and then you do average out. And that is the at least number of resources you need. If you just try to schedule them in team, you need at least this number of resources. Or it may be P4 plus P3 plus P3 and then you average out, right? So that may be the maximum number of resources, and so on. So this is the, although this particular equation look very complex and all, but essentially, sorry, here I just missed one point. So your gamma can go to 5 because here the sync node is basically 0. So I should consider till 0, right? So I missed that part, but I hope you understand. So effectively, this particular equation says that what is the average, maximum average of executing these operations, and that should be the lower bound, and which is quite natural, right? So which is basically quite intuitive also. And if you put this value of P4, P3 in this equation, it is just max of 2, 2, 8 by 3, 11 by 4, and this is basically a ceiling, so it will come 3. So what does it mean? To execute this particular behavior in this gamma equal to 4, this lambda equal to 4, I need at least 3 resources, 3 multiples. Sorry. So to achieve this latency, I need at least 3 resources. On the other hand, if you say, if I have this 3 number of resources, I can always achieve the latency 4. So it's a vice versa. So it basically, and Hughes algorithm makes sure that if you give this 4, it will, and if you give this 3, it will always able to scale, it will always use 3 only, right, to achieve this. So both MLRC and MRC is getting solved by this algorithm. Okay, so let us try to prove this, why this is correct. Okay, so I put the number, and by intuitive looks like this is correct, because but how you obtain this equation and why this particular theorem is correct, so let's understand the proof first. Okay, as I mentioned that the lower bound of number of resources to complete a schedule with latency lambda is given by this equation, and a bar is the minimum number of resource, where this gamma is some positive constant. Okay, so let us say the sum gamma. So for gamma star, okay, so gamma star, for gamma star, some value of gamma star, this particular equation give the max value, right? So this is the gamma star for which I am going to get the maximum value. So in the previous example, my gamma star will be this, right? So this is 2.66. So this is my gamma value, right? So this is coming for gamma equal to 3, right? So for this I am getting this. So for this particular example, gamma is 3. So let's say this gamma star is that, and for that I'm just getting the maximum value of this equation. Okay, and just to prove what I'm saying, just prove by contradiction. So let us assume that I have some, I can will satisfy the latency bound this lambda using some less resource rather than a bar. Okay, so a bar is something the minimum resource, but I can still have a solution of which meet me the latency of lambda using less number of resources than a bar. Okay. So that means my actual resource needed is less than of this. So this is my a bar, right? This is nothing but a bar. So a is less than a bar. So I am the resource requirement is less than my lower bound a bar. So suppose I can achieve a schedule of this lambda with less number of resources than a bar. So this particular equation is nothing but a less than a bar, and I'm just placing this a bar from this equation, right? So from this equation I'm just placing the value, and I'm just putting gamma star, because I know that for gamma star only I'll get this highest value, right? So in that particular equation I'm just putting gamma star. So till this it is clear that I can, I'm just assuming as a contradiction that I can achieve a schedule of lambda using resource less than a bar. Okay, now you just assume one thing. So suppose when you are in lth step, right? Your schedule start from time step 1, 2, 3, you are in L step. So till L step, at most how many operations will be executed or be scheduled? A into L, right? Because every time, since my A is the number of resources available, so every time you can schedule at most L you may not able to schedule all a number of resources. Sorry, I mean at every time step, you can execute at most a number of operations. You may not able to execute all a because your precedence constraint or determinacy constraint may not allow you to do that, but that is the maximum number, and you are in now L number of time steps. So maximum operation which can be schedulable till time step L is nothing but a into L, right? So now if we just assume L equal to this, I'm just assuming L is this, right? So L is this value. So L is this value. So then if I just put these things here, which is basically a into this, right? So I'm just rewriting this expression here, a into L equal to less than this, because that is what I mean. I'm just rewriting this expression because I'm just assuming L is this. So a into L is this part, which is nothing but this, right? So what does it signify? Very important to understand this. So this is what I'm saying. If I am in schedule step this gamma star plus lambda minus alpha, I know this is the maximum possible number of its schedule level, right? And I'm actually assuming that I need a resources, so which must be less than this, because that is my assumption. This a is less than a bar. So what this particular right hand side implies, right? So if we just put j equal to 1 here, it is basically p alpha, right? So if you just put j equal to 1, this is p alpha. Then if you put j equal to j equal to 2, this is p alpha minus 1. Then p alpha minus 2 till if you put gamma star, this is p alpha plus 1 minus gamma star, right? So what does it mean? So with a number of resources, till in this time step, I am considering the time step is this gamma star alpha plus 1. The operations which, so p alpha is the highest values of this alpha, you remember. So they are the longest path, right? So they are the longest distance from the sync node. So that must be less than this number. What does it mean? It is less than this number. And you understand this. So this is the highest value. If you consider the operations, all these summations, so when you're going to schedule, which are the operation is going to schedule first? This must be done first, then this, because they are the highest value, and that is how the Hughes algorithm works. So since the value is less than this number, I can assume that some of this operation is still not scheduled, right? Because it is less than, it is not less than equal to. So this is the lowest value of this level, right? So the number of operation here, they has the lowest value of level. So I can assume that this particular equation assume that, or basically ensures that at least some operation with the level is alpha plus 1 minus gamma star has not been scheduled yet, right? So this implies that at least some vertex with the level this, so not this one, so this is alpha plus 1 minus gamma star has not been scheduled yet. So they have not been scheduled yet. So that means this node has a distance from the sync node is alpha plus 1 minus gamma star. So now to schedule the rest of the behavior, at least how many time step is needed? Because this is a total length distance, and you cannot execute operations of two different level into the same time step. So you need at least alpha plus 1 minus gamma star number of time steps still, right? Alpha plus 1 minus gamma star number of time steps still needed. I am in this time step. I need this still this number of time steps. So if I just sum this plus this, what will happen? If you just sum this, this is my as a current state and this is the remaining state. If you do this, it will basically alpha plus 1. Sorry, this lambda plus 1. What does it mean? It actually contradicts my hypothesis, because I assume that I can achieve the schedule of lambda with a number of resources, which is less than a bar. But I see that if I assume that I need at least this lambda plus 1 number of time step, which is basically contradicts. What does it mean? I cannot have a schedule less than a bar, which is given by this particular equation. Okay. So is this particular proof is clear? Any doubt about this?
So could you explain the last part once again?
Yeah.
Where
Yeah.
you
So
took L equals to lambda.
Yeah. So this is very important to understand. So if I assume this, I'm just rewriting this this particular expression like this, right? So where this particular second part, this A is the resource bound, and this is the current time step, right? This is basically so if you are in time step L, you can execute at most A into L number of operations, and if you assume L is nothing but gamma star plus lambda minus alpha, so this is A into L, which is less than this value, sorry, less, not less than, equal to, less than this value, because I assume this A less than A bar, and this this particular right hand summation expire. So if you just put the value of this gamma star, it is basically nothing but p alpha plus p alpha minus 1 plus p alpha minus 2 till p alpha plus 1 minus gamma star. And since this is less than this, so among these operations, the operation which have this level, the highest priority of schedule by Hughes algorithm is p alpha. They have the highest level, they have the highest distance, right? Then this, then this. So what does this summation, since this is less than this, it ensures that at least some operations with this level, alpha plus 1 minus gamma star, has not been scheduled yet, right? So what does it mean? So their level is alpha plus 1 minus gamma star. So we need, and so that means these are the number of levels still remain. And to schedule them, at least this number of time step is needed, because I mean you cannot schedule two operations of different level into the same time step, because that is not allowed by Hughes algorithm. So it ensures that to schedule the remaining part, I need this number of time step. I am now in this time step. So total time required to schedule the behavior is this plus this. That is what I've done here. If you just do this plus this, it turns out is lambda plus 1, right? Which is basically contradicts my assumptions, because I assume that I can achieve a schedule with lambda, but it's taking lambda plus 1. So that means I need a bar number of resources, not less than that. So this is my lower bound to achieve that. Okay, understood?
Yes, sir.
Sir,
Thank you.
sir,
Yeah. Yes.
sir, like, could you go back in to the previous slide? One more previous slide further, like the before slide, 50th.
Yeah. 49 or 50?
50.
Yes.
Here, like, could you state once again what does this expression means, that the inside this thing, like sigma of p of alpha plus 1 minus j by gamma plus lambda minus, what does it exactly says? Like, is it the average number of
it's
iterations
basically is this, whatever I just in slide 40 number 49, it basically says you take the node with the highest level, you need at least those number of resources, but or you take the highest level of the next level, p4 plus p3. P4 is the number of node which is the highest level, right? And p3 is the number of node which has a level 3. So and then you take average out. So among these, which takes the maximum resource, you need at least those number of resources, and so on, right? So this expression is nothing but signifies that only, that you take this average. I mean, that's why I put this example here, just to understand the meaning of this particular expression. This expression is solved in this particular example, right? So this example, this particular expression and this previous slide expression is same, right? I'm just proving that only, the theorem one. Understood?
Okay, sir.
Excuse me, sir.
Yes.
So far we have only proved MRLC, that whose algorithm follows MRLC, right, sir?
No, I have not proved anything yet. I have just proved the lower bound. This other two proof is still remain. Okay. I just identify some lower bound. I mean, it does not prove the MRLC or MLRC yet, right? I just proved the lower bound. So now this is what this I already argued that it's a very simple and very intuitive algorithm, but it's very powerful because it's basically give a solution which is optimal one, both in context of MRLC and MLRC, right? And that is given by the next two theorems. So theorem 1 coronary is kind of another theorem. So here the theorem 2, which is actually give you the MRLC, it says that the Hughes algorithm achieves latency lambda with the resource boundaries, right? So it's basically it actually always achieves latency with this resource bound. So that means this is minimize latency under resource constraint, right? I am able to reach always lambda with a given number of resource, which is lower bound given by this equation, right? And this is actually talked about MRLC, which is basically say that It's the other way, that if lambda is, because I know for lambda, this is the resource. So this is actually dependent, right? So if I give the lambda target latency constraint, and I know this is the lower bound, and I also know that Hughes algorithm will always achieve this only, right? So when it does not use more than this resource, so I can say that this is actually also minimize the resource and give the optimal resource usage under a given latency constraint. So this is what is the other part. So I'm not proving these two in class. If you say yes, you shall show the proof, I can show it in the next class. But this is the over. But I think it's intuitive from the algorithm. You understand that it's basically it always achieve this a bar, because if you take 3, it will always achieve 4. And in other way, I mean, you are able to solve this in 3 number of resources in time step 4. So both are there. Intuitively, it is obvious, but if you want the proof, I can do it in the next class. Okay. So we are done with this today's class.
Sir?
Thank you. Yeah.
Hello, sir.
Yes. Any
Sir,
question?
like yes, sir. Sir, like when you're first explaining Hughes algorithm, you have mentioned that we have taken an extra assumption that the dependency graph will be a tree, and then we have like determined that okay, Hughes algorithm will give the best optimal solution.
Yes.
So, like where exactly like our assumption of taking it as a tree is helping us?
Yeah. So basically, it's important. Yeah, it's a good question actually. So here, because you do not, so if you take any path here, sorry, yeah. Uh, so basically, yeah, I'll tell you. So if you take any path here, the numbers are actually monotonically decreasing unit delay. So I mean, if you go to just one node to next node, it is always the number reduced by 1, right? If you take any path, so if you take this path also, this is 3210, right? So if you do not take a tree, this particular property may not hold, right? And there are, I mean, to be honest, I mean, if you can, I mean, if you ask me, I cannot answer you right now also that why, if that particular property does not hold, why it is not polynomial time. That's something, I mean, to be honest, I also don't, I mean, cannot give you the exact answer, but I mean, I can dig into and I can actually identify some counter example. I mean, you can also think yourself that if this all path have not, so this I have written here. So if you just notice here, I have written these things here. So this is the actual reason that for every path from the any vertex to a sink node with monotonically unit-wise decreasing level. So if this particular property does not hold, then you cannot guarantee the exactness of the other algorithm. Okay.
Okay.
So and that unit delay, whatever the question asked by another student, that why this delay is unit, that particular things is needed. So one solution of multiple delays, that you can assume that as a operation with delay 4 is nothing but 4 independent operation in a chain, right? So that will, there is no problem, right? Because so if the multiplier is taking 4 times step, you can assume that multiplier 1 followed by multiplier 2 followed by multiplier 3 and multiplier. So there are 4 different type of operation in chain. I can always redraw the same graph, that sequence graph. So it will still remain the sequence. I mean, it will still remain the tree. But in that case, only the first problem, MLRC, would be solved, but not the other one. That
So, but
resource, yeah.
when we are like before when we are labeling the nodes, like
Yeah.
when we are calculating the number of edges and labeling the nodes, if we want multiple delays, we can give weights to that nodes, right? No, like edges, right? Now we are only taking one edge because the delay is 1 unit. If we take, if we want to 2 3 delays, then we can like give the appropriate weight to that particular edge, and if we use the same algorithm, then we'll get the same solution, right?
Yeah, but yes, that is one possibility. And what I give the solution is, suppose this particular node has a just a minute. Yeah. So this node has a unit delay of 2. Okay. So this node has delay. So I can say this node is nothing but say 11A operation followed by 11B. Right. So that means all are single delay. So now there are 2 nodes here. Right. So this also same thing. I just put 2 nodes for 2 delay operation. 3 nodes in a chain for 3 delay operation. So it will still remain the simple graph, and I can solve the problem. Right. So this is how this. I mean, I can, because Hughes algorithm is fixed. It actually assumes unit delay. To map your multi-delay things into that, this is one possible way to solve that.
But in this approach, it's not guaranteed that 11B will be scheduled in the next cycle after 11A, right? It may be so that there's a gap of one cycle between 11A and 11B. And we can't allow that actually, right? Because it needs 3 continuous cycles to complete the operation.
No, but it is no. Basically, I will say that is uh, yeah, you are kind of right, because if say, yeah, you are kind of right, because suppose in this time step this is set 2, this is set 2, and say you have another operation was 3, so now there is another operation was set 2, so you schedule these two, say now this will become 1, right? So now you have set 2 and 1, right? So now if you may have, say, so there is another 2 is remaining, right? So suppose this also remaining. So in the next time step, you may not do this. You probably do this too. That is, if you say resource bound is true, right? That is your argument, right?
Correct, exactly. Yes, sir.
Yeah. So yeah, that is true. So yeah, so you cannot guarantee that things. So maybe you have to just tune little bit so that you make sure that, because you can ensure that so the remaining node which cannot schedule in the previous step, their value, it's the number of such node maybe was greater than a also. There is no guarantee also, yeah, because you may have, say, another 2 node also, right? So there are 3 node remaining, so you in the next time you are going to do this, not do this. So this is a problem. Yeah, you are right. So I'll actually so these questions you can also think on why this multi delay won't work, why if the delay is multiple, then why this MLRC is not solved, sorry, MRLC is not solved. Those things we can actually argue, and you can always find out some counter example. Let me think on this particular problem also. Next day we can discuss in detail, right? Okay, so any other question? Otherwise, we'll conclude the class.
So,
Yes.
sir, actually, this is a symbol graph. So
Yes.
there is no cycle or something. So what if I have a feedback in between, or if I am using a value from this fourth again in 2, so I can't use this solution, right?
No, I can't. But if you just see the data dependency graph, you in a particular operation, so usually that is every variable is basically it's SSA, right? In the single assignment. So that means that usually one variable is not something schedule. I mean, defined multiple times, or it is basically defined only one time. So if it is not, you can always rename the second definition, right? So what I'm trying to mean is this. Say suppose I understand your argument. Say suppose uh, uh, suppose you have, say, a equal to b plus c, right? So you have a equal to b plus c here, and then you are doing something here, and then again you are doing a equal to, say, x plus y, right? So now you might say that there is a second dependency and there is a loop and all, so you can just write this is a1, right? So that means one operation is exactly defined once, so then no loop will come, so the graph will remain dag, right? So that things you can assume that this is basically on, this is within one particular basic block, right? There is no control flow involved here. This is only the data flow. And if the data flow you consider as a SSA, that single assignment form, single static assignment form, the graph will always remain the DAG. But you are right, if there is a loop and all, I mean, which is, I mean, which there, then this or none of the solution will work.
Sir, if this is a big problem, how will we identify there is a loop or something?
You can do that, right? You just convert the graph into SSA. When you convert your program into SSA, actually in any compiler. So if you just go into any compiler, everything inside SSA, right? So if you just go into any compiler before any optimization, any analysis, the operations first converted into a single static assignment form. Where does it mean? One operation is not uh, defined multiple times. Okay, so it's exactly defined once. And if you have that, there is no basically self loop or any other cyclic loop here. Okay, because this graph will remain DAG. That conversion you can always do before doing the scheduling.
Okay, okay.
Okay, good. It's a good question. Anything else to any other doubt, or we will conclude the class here? I think yeah. So yeah, thank you. I think it's a good